In this episode, we're going to build a simple, reliable way to choose a statistical test quickly without guessing, even when the question is written in a stressful, exam-style way. Beginners often think test selection is about memorizing names, but it is really about recognizing what kind of question you are asking about your data. Once you know whether you are comparing groups, checking relationships, or testing whether categories behave differently than expected, the correct test usually becomes obvious. The CompTIA Data AI exam is likely to reward fast, correct matching more than deep mathematical derivations, so your goal is to develop a decision habit that works under time pressure. By the end, you should be able to hear a short scenario and immediately know which test family fits, and just as importantly, know why the other options do not fit. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The fastest way to choose the right test is to start with the type of data you have and the kind of question you want answered, because tests are built to match those two things. Ask yourself whether your outcome is numerical, like response time or score, or categorical, like pass versus fail or Class A versus Class B. Then ask whether you are comparing groups, measuring association between variables, or checking whether observed counts differ from what you would expect. Those three question types cover most of the test selection problems you will see as a beginner. If you skip this step and jump straight to test names, everything will feel like a blur because the names do not tell you enough on their own. When you begin with data type and question type, you reduce the problem to a small set of candidates. That is how you choose quickly, because you are filtering before you are deciding. Next, get clear on what it means to compare groups, because many questions are really group comparison questions hiding behind everyday wording. A group comparison happens when you have one numerical measurement and two or more groups that might differ, like model latency before and after a change, or exam scores for students taught with two different methods. The key feature is that you are not predicting one value from another. You are asking whether group membership is associated with a shift in the average or typical value. Beginners sometimes confuse this with correlation because both involve two variables, but the difference is that group membership is categorical, while correlation is about two numerical variables moving together. When you recognize group comparison, you immediately start thinking about t-tests or ANOVA rather than correlation. This one distinction eliminates a lot of wrong answers on exams. A t-test is a classic tool for comparing the means of two groups when your outcome is numerical and you want to know whether the groups differ beyond random variation. The most common beginner scenario is two groups, like System A versus System B, or control versus treatment, and a numerical measurement taken for each observation. The mental model is that you are asking whether the gap between group averages is large compared to the natural spread of values inside each group. If the groups overlap a lot and the gap is small, the test tends to say the difference is not clearly supported by the data. If the groups are separated and the gap is large relative to spread, the test tends to say the difference is unlikely to be just noise. On an exam, you do not need to compute the test statistic, but you do need to recognize that a t-test is for two group comparisons with a numerical outcome and a focus on means. There are a few important details that help you choose a t-test correctly and avoid misusing it. One detail is whether the two groups are independent, like measurements from two different sets of items, or paired, like before and after measurements on the same items. The paired version exists because repeated measurements on the same item are naturally related, and treating them as independent would exaggerate how much information you actually have. Another detail is that the t-test is usually taught with assumptions about the shape and behavior of the data, like roughly symmetric distributions and reasonable independence between observations. Beginners sometimes treat these assumptions as rigid rules, but for exam purposes the key is understanding that assumptions influence whether the test result is trustworthy. If the data is extremely skewed or the sample is tiny, the test may be less reliable, and the question might hint at that by describing outliers or unusual distributions. The main exam-ready point is that t-tests are about comparing two means for numerical outcomes, and the details refine which version fits. When the comparison involves more than two groups, a common beginner instinct is to run a bunch of two-group tests, but that creates a risk of misleading results. The moment you have three or more groups and a numerical outcome, you should think of analysis of variance, ANOVA, which is designed for comparing multiple group means in one coherent framework. The core idea is similar to the t-test idea, but instead of only looking at one gap, you compare variation between group means to variation within groups. If group means are far apart relative to the within-group spread, that suggests group membership matters. If the means are similar and most variation is within groups, that suggests groups do not differ in a meaningful way based on this data. ANOVA does not automatically tell you which specific groups differ, but it answers the fast, high-level question of whether at least one group mean appears different. For test selection, the key signal is numerical outcome plus three or more groups, which points to ANOVA. ANOVA questions can also appear in disguise, so it helps to recognize common patterns. If you see language like comparing average performance across several model versions, across multiple regions, or across several categories of users, and the measurement is numerical, that is a strong hint. Another clue is when the question suggests you are not supposed to do multiple separate comparisons, which often implies a single overall test is preferred. Beginners sometimes think ANOVA is only for complex experiments, but it is fundamentally just a way to avoid overreacting to random differences when there are many groups. This idea connects to common test-taking logic. When you make many comparisons, you increase the chance of finding something that looks unusual purely by luck. ANOVA provides an organized first step, then deeper investigation can follow if needed. For the exam, your job is to recognize the appropriate role, multiple group means, one overall test to check whether differences exist. Now shift your attention to a different kind of question, where the outcome is categorical counts rather than numerical measurements. If you are working with categories like yes versus no, class labels, or types of events, you often end up with tables of counts, such as how many items fall into each category or how counts differ across groups. This is where the chi-squared test family comes into play, because it is designed to compare observed counts to expected counts. The mental model is that you have a baseline story about how counts should be distributed, and you measure whether the observed distribution departs from that story more than you would expect from random variation. One common version checks goodness of fit, meaning whether counts match an expected proportion. Another common version checks independence, meaning whether two categorical variables are associated, like whether outcome categories differ across groups. You do not need to memorize every variant name to choose correctly, but you do need to recognize that chi-squared is about counts in categories, not means of numerical measurements. A common beginner mistake is to reach for chi-squared whenever there are two variables, but the real trigger is that the data is categorical and you are working with counts, not averages. If you have two categories and you are counting how many occurrences are in each, chi-squared reasoning is often relevant. If you have a table that looks like rows and columns of counts, where rows are one category and columns are another, you are often in chi-squared territory. The test essentially measures whether the pattern in the table is close to what you would expect if there were no relationship between the categories. If the observed pattern deviates strongly from expectation, that suggests association. On an exam, you might see a scenario where a model's predictions are grouped by a demographic category, and you want to know whether prediction outcomes differ across groups, which is a categorical association question. That is exactly the type of situation where chi-squared logic fits, because you are comparing observed categorical frequencies, not comparing numerical means. Correlation is a different tool entirely, and beginners often choose it when they see two variables, even when the variables are not the right type. Correlation is about the strength and direction of association between two numerical variables, like whether higher values of one variable tend to come with higher values of another. The mental picture is that you have pairs of numbers, and you want to know whether the points form a pattern like an upward trend, a downward trend, or no clear trend. Correlation is not a group comparison, and it is not a categorical count comparison, so it is the wrong tool for many problems that mention relationship in everyday language. Another important point is that correlation measures linear association in its most common form, which means it captures straight-line trends better than curved patterns. Correlation also does not prove causation, even if it is strong, because variables can move together due to shared influences or coincidence. For exam purposes, you want to recognize correlation as a fast check of numerical association, and you want to avoid overinterpreting it as a cause and effect statement. A reliable way to prevent correlation mistakes is to ask two quick questions. Are both variables numerical? And am I trying to describe how they move together rather than whether groups differ? If the answer is yes to both, correlation becomes a strong candidate. If one variable is categorical, like group label, you are usually in t-test or ANOVA territory for numerical outcomes or chi-squared territory for categorical outcomes. If your goal is to see whether one variable predicts another, correlation can be part of the story, but the exam will often separate simple association from full predictive modeling. Another trap is confusing correlation with comparing averages, like thinking correlation tests whether two groups differ. Correlation does not compare group means. It uses paired numerical observations across a range of values. When you keep the data type gate in mind, correlation becomes easy to place, and you stop selecting it just because the word relationship appears in the scenario. Now that you have the main tools, it helps to practice the selection logic in a way that does not rely on memorizing a decision tree. Imagine you are handed a scenario, and you must name what kind of difference or association is being examined. If the scenario is about two groups and a numerical measure, your mind should go to a t-test because it is built for that. If the scenario is about three or more groups and a numerical measure, your mind should go to ANOVA because it handles multiple means in one framework. If the scenario is about counts across categories, especially in a table of frequencies, your mind should go to chi-squared because it compares observed and expected counts. If the scenario is about two numerical variables moving together, your mind should go to correlation because it measures association across paired values. Notice that this selection logic is built from the meaning of the question, not from the words in the test name. That is why it is fast. You are matching problem shape to tool purpose. It is also worth addressing the role of assumptions and the risk of forcing a test on a data that does not fit, because exams often include distractors that ignore those issues. Many tests assume observations are independent, meaning one data point does not automatically determine another, and breaking that assumption can make results look stronger than they are. Many tests also assume the way the data was collected resembles random sampling, at least in spirit, so that conclusions can generalize beyond the sample. With t-tests and ANOVA, extreme outliers or heavy skew can distort mean-based comparisons, and a scenario that emphasizes strange distributions may hint that interpretation should be cautious. With chi-squared, very small expected counts in table cells can make results less reliable, and an exam question may hint at sparse categories to see if you notice. With correlation, nonlinear relationships or the presence of outliers can create misleadingly weak or strong correlations. You do not need to solve every assumption issue during the exam, but you should recognize when a scenario suggests the basic fit is questionable. Another common confusion is between choosing a test to answer a question and choosing a metric to describe a relationship, because learners sometimes treat them as interchangeable. A test like t-test or ANOVA is designed to support an inference decision about whether observed differences are likely due to chance under a baseline assumption. A descriptive measure like correlation describes how tightly two variables move together, which can be used as evidence, but is not the same as asking whether group means differ. Chi-squared is an inference tool for categorical patterns, but a simple percentage difference can be descriptive without formal testing. Exam questions often signal whether they want an inference decision by using language like statistically significant, hypothesis, or evidence, but they can also ask you to choose an appropriate method without those words. Your safest strategy is to match the test to the structure of the data and the structure of the question, then treat the result as evidence with uncertainty, not as a final verdict. This keeps your reasoning aligned with how these tools are intended to be used. Speed on exam day comes from building a mental checklist that runs automatically, and you can make that checklist very short without losing accuracy. First, identify whether the outcome is numerical or categorical, because that single choice narrows the field dramatically. Second, identify whether you are comparing groups, checking category counts, or measuring numerical association, because that aligns directly with the core tests in this lesson. Third, count how many groups are being compared if it is a group problem, because 2 groups suggests t-test while more than 2 suggests a ANOVA. Fourth, if categories and counts are involved, think chi-squared. And if 2 numerical variables across paired observations are involved, think correlation. These steps take only a few seconds once practiced, and they prevent you from being seduced by answer choices that sound sophisticated but do not match the data type. The exam is often less about doing the math and more about showing that your method choice is coherent. To bring everything together, choosing the right statistical test quickly is about reading what the data is and what the question is asking, then matching that to the purpose of each method. You learn that a t-test fits 2 group comparisons with a numerical outcome when you care about whether the means differ. You learn that ANOVA fits numerical outcomes across 3 or more groups when you want a single overall check for mean differences. You learn that chi-squared fits categorical count data when you are comparing observed frequencies to expected frequencies or checking whether 2 categorical variables are associated. You learn that correlation fits paired numerical variables when you want to describe how they move together, while remembering that association is not causation. When you practice this matching based on problem shape, you will feel your speed increase without sacrificing correctness, which is exactly what time CompTIA questions demand. With this foundation, later topics like confidence intervals, regression interpretation, and classification metrics will feel more connected, because you will already be thinking in terms of which question you are asking and what evidence is appropriate to answer it.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.